solve the partial differential equation for steady state temperature distribution in a cylindrical solid with certain boundary conditions satisfied. So we'll solve that problem. So the problem that we want to study is the following: steady state So what we have is semi-infinite solid cylinder. Okay, of dimension. Let's say the radius of the cylinder is A. All right. And the bottom part of this cylinder is held at temperature T naught, and the curved surfaces are at and bottom surface at T equal to T naught, and we are interested in steady state distribution. Okay, so that's what we are interested in. So since a steady state distribution, the diffusion equation will become Laplacian equation. Okay, the heat diffusion equation is normally given by diffusion equation, but under steady state temperature condition, all I have to calculate is, if U represents the temperature, I have to solve the Laplacian equation as usual. Okay, so the only difference here is we have to use the cylindrical geometry. So the independent coordinates will be rho, phi, z. Okay, so basically rho is projection of any position vector in the xy plane, right? Wherever it is a projection on this. So rho is that for that point P. So so that is the one thing, and then what are the boundary conditions? So basically, what is the boundary condition in this for this problem? We have what, rho at if the independent coordinates are rho, phi, and z. For any rho, phi, z equal to infinity, the temperature has to go to 0. That we can write down. The other boundary condition is, let us say, rho equal to a, any phi, any z, and I can write rho at any rho, because that's a solid cylinder, so it could be any point within the cylinder, right? This rho is, in this case, rho is equal to a, but if it is, any point within the solid cylinder, and phi, z equal to 0. These are the thing. So what is this? Rho at a, phi, z. What is that? What's the boundary condition? Because the important thing is to identify the boundary conditions first correctly. Rho equal to A means what?
It's on the edge.
On the surface, right, on the cylinder. So we are saying it is held at 0 degrees. So I'm going to put that as 0. And rho at z equal to 0 is the bottom of the cylinder. It's at T naught, right? So constant temperature. The other thing which we have to realize is this is a cylindrical symmetry. So every cross section, whatever it is, here it's T naught at infinite, z equal to infinity becomes 0, but different in the cross sections. Each cross section will have the same temperature, and the temperature will be spherical. It will also be actually symmetric. Okay. So we also have the last condition will be the boundary condition will be U represents temperature, right? Temperature will be is actually symmetric. And each cross section would have the same temperature distribution. Okay, so these are the condition, and okay, let's keep that there. I can discuss this in this itself. Yeah. All right. So what is del square U for the cylindrical coordinates? How do we write that? So this is the equation we are solving, although diffusion equation is del square U is 1 over D, okay, where U represents temperature here. So what is del square? You remember how to write del square?
We did it in the beginning. We did it in the beginning.
Right. So in any curvilinear coordinates, del square, I'm going to call it V, is written as what? 1 over h1, h2, h3, right? Partial with respect to the first independent coordinate, in this case will be rho, h2, h3 over partial V. In this case, your temperature is U, but I didn't want you to confuse between U and U1, so I'm just giving you right like that. Partial with respect to U2 of H1, H3 over H2, partial V with respect to U2, plus partial with respect to the third independent coordinate. So what is that? H1, H2 over H3 partial V with respect to U3. This should be equal to 0. All right. Now, for cylindrical coordinates, what is U1, U2, and U3? And what is H1, H2, H3? We had derived the scale factors and all that stuff.
Rho phi z and
Yeah,
one
U1.
rho 1.
Yeah, let's write down that. U1 is rho, U2 is phi, angle phi basically, okay. U3 is z, small z is the independent variable. H1 is
1.
1, H2 is, and H3 is 1. Okay. So we had even derived why we get these scale factors and all that. Okay. So all I have to do is write del square for the, because it has got cylindrical geometry, I will write del square like expanded properly. So del square u is nothing but 1 over rho, right? Partial with respect to u1 is, rho is the independent variable, h2 is rho, partial of, I'm calling u, right? U with respect to rho, okay, that is my first term. Partial with respect to u2, u2 is phi, the azimuthal angle. H1 is 1, so rho is in the denominator. Partial u with respect to phi plus partial with respect to z of h1, h2, h3. So rho is in the numerator this time, right? Partial of u with respect to z is equal to 0. Rho is outside also. 1 over rho is multiplying all the terms. Just check that is correct and then we'll erase this now. Partial with respect to this, h2 is in the numerator, good. Others are 1. Rho is in, h2 is in the denominator, and I have to take this. Partial with respect to z, h2 is in the numerator this time. Okay, alright. So I'm going to erase this, okay. So the only thing different is the same Laplacian, but del square has to be written for the cylindrical coordinate system. So this is the equation we have to solve now. Let me take 1 over rho inside because otherwise I'll forget it. Let me just put this here. Okay, because that is common for all of them. All right, what is the next step? So this is still a PDE, right? I mean, so how do we convert this into ODE? Ordinary differential equation?
Separate the variables.
Yeah. So we're going to say u rho phi z is going to be product of 3 functions. P as a function of rho, phi as a function of phi, z as a function of z. Okay, so that will lead, convert this equation into ordinary differential equation. So let us do that. So the first term, since the function of rho only, phi and phi z can be pulled out. So I have 1 over rho. Now I'm making that as a full differential, and I can, phi z can be pulled out, right? Phi z can be pulled out, rho is in the denominator, and then rho dp over d rho. Now they're all full differentials, okay, plus 1 over rho. This time I can pull p and z out. P, z can be pulled out, and I have got a rho in the denominator, full derivative with respect to phi of 1 over rho. That rho I can pull it out, I can put it as rho square, and this can become now d square phi d phi square. Let me put like this, so that's the function, and with the one without the bar is independent variable, plus so in this case I can put p and phi outside, rho and rho will cancel, and I can write that as d square z dz square equal to 0. All I've done is just plug this in, and since it's a function of z only, p and phi are function of rho and phi, so we can pull those functions outside, I'll have a row in the denominator, but this row can be pulled out because it's not, doesn't depend on z. This row and that row will cancel, so I have this. Okay? Is this correct? Rho square. Okay. All right, what is the next step? So we have this is a ODE you got already. So separation of variables, you've done. Okay, what's the next step? We want a differential equation only in P, differential equation in phi only, differential equation in Z only, right? I mean, so we just divide by first P phi Z. Okay, so let us do that. So divide by P phi Z. So I will have the first equation will be 1 over P. I also have 1 over rho, it looks like, d rho of rho dp d rho. Okay, P phi Z, so I have 1 over rho square, the function phi, b square phi, b phi square, okay, 1 over z, the function, d square z, dz square equal to 0. All right, all of them have become now normal, not PD anymore, full differentials, right? Okay, what is the next step? Because this is what we need to find, right? I mean, this is a solution we are trying to seek subject to all these boundary conditions. So we need to find solving this for that problem subject to these boundary conditions. All right, so what's the next step? Is there any term which is function of one independent variable only? Second term is mixed.
Separated?
Yeah, the last term is easiest to separate out because here we got things mixed up, so we have to. So let's just separate this one out. So I'll take you to the right hand side. So if I take it to the right hand side and get rid of this, so what can we say? This is a function of rho and phi, and this is right hand side is a function of z only. And we say this is not possible unless each one of them is a constant. So the whole idea is to get the separation constant correctly based on the boundary condition for this problem, right? Okay. So I can get rid of all these things. All right. So I'm going to say, okay, this is some constant, separation constant. Now, when we did initially, we just put plus or minus, we were just guessing without any reason. Now, we have now very specific problem, and I can guess that I should choose positive separation constant or negative separation constant. Okay. Okay, so what happens if I chose, you have to decide which is the correct one, right? Should I choose this or should I choose this? Which one should I choose? If I chose this, what is the solution? Z as a function of Z. Here, what is Z as a function of Z? And so that will tell me which sign I should choose. And so easiest is how the behavior of Z is same as behavior of U at Z equal to infinity, right? So, yeah, so which one should I choose? At Z equal to infinity, it has to be 0.
The second one,
Second one,
because you don't want it to oscillate.
because first one is oscillating solution, okay, exponential ikz plus this thing. So we have to choose a second one. So exponential of, this will give me solution. Okay. Both are, again, this is possible, but because we want Z at Z equal to infinity to be 0, we'll put A equal to 0, because this we are going to drop off. So if you don't remember it, I mean, just always, do the, this is some, you just take the derivative 2 times and check whether it's a solution or not, okay? I mean, and that will be an oscillator. Which one gives you plus k square minus k square? You got only 2 options. Okay? You can put it as sine kz if you want, but if you've forgotten this is your harmonic oscillator thing, just try both of them, right? I mean, try this as a solution, and right hand side should be equal to left hand side, and try this as a solution, okay? I mean, plus k, it doesn't matter, plus, minus, I mean, you try both of them, and if you've forgotten, but anyway, you should start recognizing this form. When you have d square y over dx square equal to minus omega square x, that is an oscillating solution, whereas the other one is either exploding or decaying solution, okay? We cannot have exploding solution at z equal to infinity, it has to become 0. Okay, so this tells me I have to choose this, right? I mean, we cannot have both. We have to take that. So this whole thing is negative k squared then. So I can now replace this as negative k squared. All right. And I can bring it to the other side also now, okay? So plus k squared equal to 0. So my original differential equation has become that. All right, it was a right-hand side. Now I bring all the terms to one side. Now, what is the next step? What can we do? So I'm going to say, I know the form, but I don't know the constants. That's the whole idea, is to get the constants correctly. So this is of this nature. Minus kz, okay, with the a or something, we'll decide whatever. Okay, what is the next step?
Now you separate rho.
I can easily make this a function of phi only by multiplying by rho square everywhere. So it's a separation of, you have to remember separation of variables method, everywhere we're separating e. So multiply by rho square. Okay, so that will give me rho over p of the following. Rho plus 1 over phi d square phi d phi square plus k square rho square equal to 0. All right. So now this is a function of rho and this is a function of rho. It is this term I can pull it to the right hand side. right? And say, so what I have is then rho all right. So again, this we're going to put as some constant, okay? I used A, right? So this is all right. So if I call this as a separation constant m squared, I don't choose negative because there's no way, phi doesn't become infinite. There's no way I can make it. So that has to be positive. So I have that as m squared, and I got the function hanging down. I don't want a differential equation should be, last term should always be what? Something y, right? D square y over dx square dy dx plus y. So it is like p is that, right? It's a function. So I'll bring k m squared to this side and multiply by p so that it looks like a normal differential equation. Okay, so bring this to this side, minus m squared equal to 0. And then I'm going to multiply by p. So this p will go up here. So it looks like a differential equation. So this is your differential equation in rho. So if you expand this out, how does it look like? It looks like what? Rho square d square p over d square, right? Then I have rho, first derivative of p with respect to rho, plus k square rho square minus m square times p equal to 0. So this is a second order differential equation, right? I mean, so it looks like x squared. Let me put this like that so that that's a function. All right. So what is that differential equation? These are simple differential equations, so you can guess what is that differential equation. Think of P as y or something, and rho as x. Have you come across this before? I'm going to write it like this, whether you can recognize.
Bessel?
Bessel
Bessel.
functions, no, normal Bessel differential equation, right? So the solution of that we would write as J sub n x, right? The solution of this is J sub n, whatever that number is, and whatever is this independent variable is, right? So here, our solution is J sub m. So your P of rho is really, it's got two parts. Okay, let me call it as C, J m, K rho, let me call it. And what's the other part? It's second order differential equation, so it must also have two solutions, right? Everywhere, I mean, that's why we have plus minus, right? Both solutions are mathematically possible. Use some constant times. What's the other one? Most general, if m is not an integer, of course we could put j minus whatever that number is, j nu, j minus nu, we could have done it. But otherwise, most generally it's Neumann function, which is always blowing up at rho equal to 0. So we just eliminate that because it doesn't exist. Okay, I mean, so I think we use the symbol y, right? I mean ym k rho, but rho equal to 0, it becomes infinity, therefore we have to put the constant f equal to 0. Okay, so this doesn't exist, should not exist. F must be forced to become 0. So just as everywhere you got sine, cosine, or whatever it is, we have, this also has got two solutions because it's a second order differential equation, so it must have two solutions. One of them is the Bessel function, the other one is the Neumann function. But Neumann function at rho equal to 0 becomes infinity, so that's not possible because we do have, in this case, at rho equal to 0, at bottom temperature is 0, it's not infinity or anything. So f has to be 0. So the only solution that you have, physically meaningful solution, is just the Bessel function here. Okay, so we have something at this point, but we have to now start applying all the boundary condition, right? I mean, I'm going to call Jm k rho. Okay, it's the same k, which is the separation constant that we had. And this is, right now, looks like a combination of something. I'm just, the shorthand notation I'm using, a sine m cosine m phi. Okay, I'm just going to call it something of that nature. This is what it looks like without applying any boundary. We applied only one boundary condition. This is the only one we have applied. We've not, which gave me this. Okay, but I have to further, use many things at this point. Okay. So which one should be applied next? At the curved surface, the temperature is 0, right? Can we apply this one and see what happens? What it tells us? Okay, so u at 0. So this implies, that is one thing that can do that, and there's also temperature is actually symmetric. Let me maybe do that first. So I said it has to be actually symmetric, and every cross section, it has to be the same, whatever the temperature distribution is. So this solution it is not changing, as you change phi, it is not, temperature is not changing. How is that possible? Under what condition will that be true? So I'm going to get a condition on M based on that boundary condition. How is that possible? actually symmetric, and it isn't, m has to be 0 actually, otherwise I cannot satisfy that. It has to be exactly equal to 0 to get rid of the dependence on the azimuthal angle actually. So m has to be 0. So m has to be 0 means this m is also now J0. Not all Bessel functions are contributing for this particular problem with boundary condition. Because of this, m has to be 0. Okay, so I have the solution is basically some constant. We'll come to that at this point. I mean, there's a constant e times a or whatever it was. Okay, we'll get that constant. This is what it is. Now, this boundary condition number 2, if I apply, we apply now 1 and 4. So if I apply this condition, what does that tell me? U at rho equal, that is on the curved surface, any phi and z equal to 0, that implies J0 at rho equal to a has to be 0. Okay. So this condition number, this boundary condition number 2 tells you the Bessel function of 0th order must satisfy that condition. Now, do you remember a Bessel function? I mean, we derived it. Okay. This is a general expression, but I need only J naught. But just to remind you, we got this from the Frobenius series method. Okay, that's my Bessel function of nth order. But if I want J0, Z, it's an infinite series, which is given as 1 minus Z squared. All I have to do is n equal to 0 and then write this series. I think we did it in the class. We got J halves and J zeros. Those are the only ones we did. So it is an oscillating series like that. Okay. So J0x all right, it starts at 1, I think. Okay, z equal to 0 is 1. Okay, it starts at 1 and it sort of oscillates. So if it has to be 0, we also know it is 0 at several locations. You just have to numerically, in fact, calculate this, okay, and do the convergence and all that stuff. So J0's Bessel function of 0th order as function of z looks like that. It's an oscillating solution. Not like the way like a simple harmonic oscillator, but it's still an oscillating solution. And we know where these Bessel functions are 0. At what values of z this Bessel function becomes 0. Okay, and what does that tell me is the following. So for us what it tells me is condition on Ka. So it doesn't allow all k's. When we had this k, at that point we did not know what k should be. Now it gives me further restriction. It does not allow all k's, or it allows only certain values of k for which this becomes 0. Okay, so that I know by just plotting J naught x over x. And I believe I also said that in the class previously, where it becomes 0. So the location at which it becomes 0 are 2.4. It's really funny values, but it is what it is. Okay. All we know is it is not continuous. We have to satisfy. It becomes discrete. Basically, Ka is. It becomes, there are several values of k for which it can be satisfied. So it is, you have to sum over k. That's how I'm going to come to superposition principle also. So this becomes 0 for Ka equal to several values, 2.40, 5.52, and 8.65. So these are really numerically done, or we have basically k is now discrete. It's not continuous variable. Okay, so k it's a discrete one. So it is, k could be, k1 is 2.40a, at which Bessel function of 0th order will become 0. K2 is when, and so on and so forth. Okay. So what it tells me is now, I have to make this now sum over all the, because there is some single value, several values for which it becomes 0. And so I'm going to now put an index n here, okay, and n here, and I have to sum over the sum of the constant should also now, I'm going to call it an, or a, you can call it something, doesn't matter, an. Sum over n going from 1 to infinity. N equal to 1, it will take that value. Okay, Kn is exactly equal to 2.40 divided by the radius of your cylinder. Okay, so there are several values of k, discrete values of k, for which is going to become 0, your Bessel function. So I have to, the real solution is superposition of all those values of k. Okay, it's sort of the quantization kind of principle happening. It is not, only certain values of k, it becomes 0. That kind of a principle always comes. Okay, so this is a solution I need to now find. Okay. Okay. So we don't have phi because n equal to 0, so we don't have to do that. So my solution that I'm seeking for this problem is the following. I'm going to write down so you can see that. An J0, only, this is the only Bessel function which survives. Kn, was it A, right? Was it A?
A row.
A row is there, right? Okay. Okay, A was there, okay. Kn row, exponential of minus Knz. Okay. And going from 1 to infinity. Now, as I told you, the biggest problem is always getting this last coefficient in all these problems. And for this problem now, what can we use now? I need to get, so I have used that. Okay, I need to get one more thing, right? I have not applied this boundary condition. So if I apply the last boundary condition, what do I get? This is a solution I have to get, okay? But I have to calculate A sub n. That is my goal now. And I know what Kns are. Kns are precisely this, okay? This I know exactly what it is. We do know that, but we need to now calculate that. So Z equal to 0, the temperature, bottom right of the cylinder, temperature is T0. I can write T naught equal to summation An J0 Kn rho n going from 1 to infinity, right? I can do that. So I'm further simplifying to get my A sub n, and I'll come, once I determine that, I'll have to come and plug my An from there. Now what else can we do to calculate now An? Now that you got here, this is what we applied the fourth boundary condition also. I need to extract out this. You have to learn this trick all the time. I mean, when you have something coefficient, something function, and you have to extract, what do you do? If it's in Cartesian coordinate system, you will try to use Fourier series method. Okay. In special functions case, you have to use the orthonormality properties. Okay. So that's why we have to know all the properties of the different special function of normalization and orthonormal property. We have to know. Okay. So if it's supposing we know the radius of the cylinder is a, supposing I multiply this by kr rho, let's say 0 to a. I need to maybe do one more trick perhaps. Yeah. Because let me write down the orthonormal property, then becomes clear why I have to use that trick. All right, the orthonormal property of Bessel function is like this. If I have 0 to a, so what is it for alpha not equal to beta? That you should be able to guess. And why do we have x here? So for alpha not equal to beta, this should be 0, right? I mean, but alpha equal to beta, that's a normalization property, right? So what is the, why do I have this?
The weight. The weight.
It's a weight because Bessel differential equation is not Sturm Liouville. So we have weight. So in this in like Legendre polynomial will not have it, right? Plx Pmx dx is equal to 0, and p square Lx was 2 over 2 something, some normalization is there. So first I want you to, this is the simplest case. First you have to understand I have x, mainly because that is your integrating factor to make the Bessel differential equation putting into Sturm Liouville form. So that's what you have here. Okay. So this is the case for alpha not equal to beta. For alpha equal to beta is a normalization condition you will get, and I'm going to write down now more generally because you can understand that. So this is equal to whatever that is, okay, j square mu plus 1 alpha a, okay. So for, and then this I can put delta alpha comma b, okay. I've combined normalization and orthonormalization property in one expression. When alpha equal to beta, this is 0. When alpha is not equal to beta, this is equal to 1, and you have that equal to this expression. We had not proved this, I think, but it is in your book. I think it's page 610 or something like that. For each of these special functions, you will have some property like that. So it is. So if that is the case, what I want to do is what I was trying to say is what is that? I'm going to multiply. I just cannot just blindly. I have to put the weight factor also. Okay, my independent variable here is rho, so I have to multiply by rho j0 kr rho d rho. I'm going to multiply right hand side and left hand side by this summation a sub n going from 1 to infinity of this integral j0 kn rho j0 kr rho d rho. Okay, so that's the weight factor I'm getting because Bessel function is not a Sturm Liouville form, so it has some weight factor, and for this, so this is my independent variable, so it becomes rho d rho. So this is what I'm going to do, and then I'm going to apply this property to the right hand side and try to get an. Okay, so what is this now? So I've given this for you. And for us it is J0, right? So what we have is 0 to A, J0, so row, so I needed, so let us say Kn row, Kn row, D row is nothing but A square over 2 of J square 1 of KRA. KM, KR. Did I put AR? Okay. So I put it as R. Okay, let us call it KN and R. Okay, so this is for me delta n comma R, whatever that index is. All right. So what happens is, so this is, so let me also put here maybe that then it becomes easier for you to understand. So delta n comma R is there. So n, so this is nothing but A sub R of all these things, right? A square over 2 times Bessel function of first order square KR A. Okay, so I have extracted it, but I still have other things to do because it's still not so useful. So what I have is AR, the coefficient that I want is nothing but 2 times temperature, whatever that is, A square, the radius of the cylinder, Bessel function of the first order evaluated at KR times A times this integral. I'm still having some integral that I have to evaluate. Rho is there? Okay, so this is what we are trying to do. First, I apply the orthonormal property, but I'm ending up with the integral, which I have to again use calculate using the properties of Bessel functions that we had done in the class. Actually, let me just get that expression for you. When we did the generating function, we had, some recursion relationships and some properties. One of the properties that we had proved using the generating function is the following: d over first derivative of this quantity is nothing but z mu j mu minus 1 z. This we just got from generating function. We apply the property, multiply by g, we just got it from direct from the series expression that we had. We proved this. Now, what do I have? I have this integral to prove. So let me put z equal to kr rho. That's I can do easily in that expression. And I can put nu equal to 1, perhaps. Yeah. So let us see if this was first nu equal to 1 will be this, right? Yeah. Nu equal to 1. This is J0Z. And then let's put z equal to kr rho. And what do I get? dz is, kr is some constant, kr d rho. So, so this is d over d rho over dz. D rho over dz is 1 over k sub r. Okay, so this is nothing but you differentiate with respect to rho, and then I have to multiply with d rho by dz, which will be give me 1 over kr. Z is nothing but kr rho j1 KR rho is nothing but this is KR rho J0 KR rho. Okay. So this KR and that KR will cancel. That is not a problem. So I have the following expression which I'm going to use. I have d over d rho of rho times J1 KR rho. This expression is nothing but KR okay, I don't need that. Okay, this is nothing but KR rho times J0 KR rho. All right. So what I need to calculate is this quantity, right? I mean, so if I integrate, I need to get the integral of rho J naught KR rho d rho. So integrate both sides with respect to rho. Okay, and in the limit 0 to a. Okay, so we will do the same thing. So when you integrate this between 0 to a, since it's a total differential, so what we have 0 to a of this integral is simple now. Rho J1 KR rho d rho is equal to KR of this whole thing, 0 to a rho J0 KR rho d rho, which is the right hand side that I want, right? I mean, this is what I want to evaluate that, which is nothing but 1 over KR of all that stuff. But let me first, so what is this expression? This is very simple. Because it's total differential, it is simply rho J1 KR rho evaluated between 0 and a, right? This is nothing but equal to KR of 0 to a of rho J0 KR rho d rho. Okay, and for rho equal to 0, this lower limit, because of that, will become 0. So what you have is a times J1 KR a. So this expression becomes a times J1 KR a. Only in the upper limit it's contributing, is k sub r of this integral 0 to a rho times J naught KR rho d rho, or this integral is simply 1 over KR of all that stuff. So this is nothing but this integral is nothing but 1 over KR of a times J1 KR times a. Okay, so that integral is that, and we can simplify the coefficient of AR. That we need is nothing but what I have is 2T0. A and A will cancel, so 2 the constant temperature, A square is here, A is there, so this is looking like that. This is J1 square, so I have a J1 KRA, because so part of this will cancel with that, and I think I have 1 over KR also. Right? Yeah. So our the complete solution is then for this problem is then this. We go back to this expression, all right? This is what the last, as I said, this always getting this coefficient is a major pain in the neck. Okay, so this is AR, so all I have to do is, I have that as AN, so I'm just going to change AR to R to N. So AN is simply 2T 0 over A, 1 over J1, KNA, 1 over K sub N. So my complete solution is simply N going from 1 to infinity of all these things. Okay, I can remove this out because this doesn't depend on N, that doesn't depend on N, but the rest has to be inside. This is J0 of Kn rho. Here it is J1 Kna, which is a constant in some sense. And I have a 1 over Kn is also there. And exponential of minus Knz. And as you know, Kn has fixed value, something was 2.4, K1 was 2.4 over A, K2 was something, 5 point something, 5.2 A or something like that. So you have to calculate this for each one of them, right? I mean, it's going to change for each value of N, right? That is, and you know, and then you have to do it. So it's a pretty complicated solution. So what I want you to realize is calculating these coefficients are not trivial. You may get the general form is got a Bessel function and decaying solution, fine. But you know, the actual magnitude, by how much is weighted, this is not easy, not at all trivial to calculate, and that's why we learned all the properties of orthonormal properties of Bessel functions. Of course, these days you got computers, so you will perhaps you will just start from del square U and start doing the problem. But still, you need to check that your numerical algorithm is correct by doing some extreme limiting cases, so that you can compare, what turn numerical algorithm you will get from del square. There are several methods for relaxation method and stuff like that. There are a lot of numerical methods. So whatever you do, at least for one case, limiting case, you have to check that they do indeed get the same result. Then you can, you can keep changing boundary condition, whatever complex. It doesn't have to be, two sides zero, whatever. You can now make the problem more general numerically, right? But I just want you to understand why we were doing all these properties of special function is mainly to solve completely a PDE problem. You need to know many things, but numerically, if you're doing, you don't have to do many of these things at all. You can just do it. But of course, you can also give nonsensical result algorithms. They're not converged, so you have to check them. So I wanted to do one problem completely so that you appreciate. It started out simply, but then it soon became so complicated, right? So that's you have to know lots and lots of properties of this, whatever the problem is, right? If it's spherical coordinates, it could be associated Legendre polynomial and spherical Bessel function, not this Bessel function, but the other one. So you need to know the properties. The minimal is orthonormal property. Once you know that, you can at least try to calculate the coefficient by multiplying by Bessel function of different order and doing the limits, and get the integrate both right hand side and left hand side and extract out the coefficient. That's the typical trick that you do. But if it's Cartesian coordinate, we can do it by Fourier series or Fourier transform. Okay? That will be a little bit easier. But other coordinate system is going to be pretty messy. The exact solution of PDEs can be pretty messy. So that's the message that I wanted to pass on to you. But physics has got nothing but PDEs, so that's why we need to learn some of these special function and the properties. Okay? All right, so I'm going to leave you with this message today, and maybe I'll give you a homework problem on a PDE problem, so that at least you understand how to use it. All right? Yeah.